Oh, I was just gonna, let me just introduce you for just one second.
Okay.
So Ewin Tang from University of Washington, and I guess she's going to say what, so she's going to tell us about joint work with Jongwon Ha and Robin Kotari, and I'll let you say the title if you want.
Okay. Yeah, thanks to the organizers for inviting me. I'm going to be talking about this work that I did this past summer while I was at Microsoft Quantum. There is not yet, it's not yet on arXiv, but if anybody's, but if you want a copy before exclusive pre-release copy, feel free to email me. Okay, and the topic of this talk is the problem of Hamiltonian learning. So the setup here is that we have an n-qubit Hamiltonian, and then we assume that it's L local and in some ambient dimension D. And these are both constants, D and L, so we don't have to worry about them. You don't have to worry about them if you don't want to. And here, our Hamiltonian H is a sort of linear combination of terms where the coefficients are valued between -1 and 1. And the terms are just basically, they're just local terms. So they're operators on n qubits that have support that's at most L and have operator norm at most 1. So in the example here, right, just for the sake of being really explicit here, I'm working in a, for this example, I'm in a one-dimensional space because all of the qubits are in a line. And the terms are all acting on adjacent qubits. So here, like the E2 term is basically something that looks like the identity here, and then some operator on these two qubits, and then you tensor the identity on all the other qubits. This operator here can be anything, but we're just going to assume that we can write it in the Pauli basis. And so we assume that these EAs are distinct products of Paulis. So for example, this could be like a tensor Y or something.
So just a quick question to clarify D. So D is a spatial dimension. So D is 1 is a line, D is 2 is a grid.
Right.
It's not, okay. For a moment I thought it's qubit dimension. Okay, thanks.
No, yeah. It's the spatial dimension. Okay. And
you're not allowing sums of the same tensor products of different Paulis on the same couple of qubits.
I am. I just want the EAs to be distinct. Does that make sense? Yeah. Okay. Given all this information, we can define the Gibbs state at an inverse temperature beta to be this quantity here, this rho. And I'm going to think about it as like a function of the coefficients, so as a function of the lambda. And this is what I've written here, the exponential of minus beta h, just normalized by the partition function, which is the trace of that, to make it a density matrix. And so the problem is that we assume that we can prepare copies of this Gibbs state. And this can, and we assume that we have some system, maybe like in the lab or something, that we can prepare the copies of a Gibbs state for just by, I don't know how physicists do things, but presumably you have some system and then you let it equalize at a certain temperature, stabilize at a certain temperature, and then you get some Gibbs state. And the goal is to sort of learn the Hamiltonian from this. So you know the EAs, and then the goal is to learn the lambdas, the coefficients. And these terms that the things that we care about are both the sample complexity, so the number of copies of the Gibbs state that we use, as well as the time complexity, which is the time it takes to compute the coefficients after we're given all of our samples. And something to note is that this problem is going to be hard as we take beta going to 0 and as beta going to infinity, because as we take beta going to 0, then this Gibbs state becomes the maximally mixed state. So we lose information, or it gets harder and harder to learn the coefficient information in that respect. And similarly, as we take beta going to infinity, this converges to just the ground state. So it converges to the ground state of the Hamiltonian. And this also is makes it not possible to get the information of the coefficients again. And so something to note is that the time complexity here, the best result that this time complexity can be is the optimal sample complexity times the length, or times n, which is the length of a sample. So if you have a sample complexity of s, then the optimal time, if the optimal time sample complexity is like s, then the optimal time complexity is going to be like n times s, because you have to read all of your input in order to output the coefficients.
So I have a question.
Mm-hmm.
So in the regime when beta is infinity, if the task was, let's say, given a ground state, output one of the Hamiltonians of which x the ground state, could that be easy potentially?
I don't know enough about this. I was sort of hesitating. I wasn't sure what the right statement is in this respect.
I see.
Yeah. If somebody else knows the answer, feel free to chime in. Okay, any other questions before I move on? Okay. So another reason why we would study this Hamiltonian learning problem, apart from it being like a pretty natural problem in the quantum setting, is that this is also well studied in the classical setting, which I'll get to in a little bit. And so we sort of know the right bounds, or the right sample complexity and time complexity in the classical setting. So here in particular are the sample complexities and time complexity of Hamiltonian learning, if you assume that the Hamiltonian is classical. And you see that as beta goes to 0 and as beta goes to infinity, you do have that this blows up. And similarly, there is a sample complexity lower bound. It's for like a slightly different problem, but this is sort of suggests that the sample complexity upper bound and the time complexity upper bound are both optimal. So we understand what happens in the classical setting. There's a recent work by these 4 authors here, that's in Nature Physics, that tackles this problem in the quantum setting, and then provides a sample complexity upper bound and lower bound, which I've given here. And they don't give a time complexity upper bound, so it's not known whether you can solve Hamiltonian learning in polynomial time in general. But they do give an algorithm. They do sort of assert an algorithm that runs if you assume that the input that beta is bounded. So this is the high temperature regime. And so here we assume that we assume that beta is bounded by some critical temperature beta C, and they don't give an explicit runtime, but I'll just naively, how I got this was just by taking the sample complexity and then just assuming that the time complexity must be larger than the sample complexity of their algorithm. And then here, this exponential goes away because beta is bound. And here, so here C prime and C double prime are all just constants that are greater than 0. Okay, so given that it seems like, based on the difference between quantum and classical, that there could be still gaps left in all three of these I guess problems, or in these complexities.
Just, can I ask a question? I'm a bit confused by the parameters. So for example, the classical upper bound, if I just take beta equals 1, so what does it mean? It means that using log n samples from some distribution, so the Gibbs distribution for you can recover the whole Hamiltonian?
Yes.
Okay, so this distribution is very, very concentrated or so. Yeah, so
I mean,
each sample, I can see that each sample gives you n bits or something. So it's not, it's information theoretically, it's possible.
mhm. I'm going to explain how you get this upper bound.
Okay,
It's
good.
straightforward.
Then that's fine. Okay, thanks.
Yeah.
For the quantum time upper bound, what if you take beta go to infinity, which is at a low temperature limit, this problem becomes simple?
No, so this only holds if you take beta bounded.
Okay.
Yeah, sorry. So this is like, we're trying to be efficient here with the labeling, but yeah. Okay, right. So that's the state of the world. This is the state of the world, and then what I'm going to talk about is our work that sort of closes this question in the high temperature case. So we take this sample complexity lower bound in the classical setting, and then we extend it to this problem. So we translate it to this Hamiltonian learning problem, and then we show that we get a sample complexity lower bound, and then we show that it's tight in the low temperature case. And also we give an algorithm that gives optimal sample complexity. And so, yeah, so the only thing that's not optimized is that the critical temperature is constant, but it's not like, we don't try to optimize it. Okay, so first I'm going to talk about the classical setting. So I'm going to talk about how we get these sample complexity upper bound in the algorithm. So in the classical setting, what the task becomes is the task of learning the parameters of a Markov random field. So what we do is to get the classical setting, we restrict to diagonal Hamiltonians H. So in particular, we have just products of polys that are Z's and I's. And then in this case, the Gibbs state is also diagonal. And so, or sorry, the density matrix of the Gibbs state is diagonal. And so the Gibbs state is just a sample from a classical probability distribution. And this probability distribution, if the Gibbs state, if we're looking at a Gibbs state, is called a Markov random field. It's just like, it's the definition of such a thing. And in particular for the ease of exposition, I'm just going to consider the Ising model. So here we have some graph, or I guess a lattice here in 2 dimensions. And what we do is we just take terms to be, so one of these edges represents a term that's just Z on the adjacent qubits. And in this setting, it's easy to see, like, if you could just work it out that if you reparameterize the basis states as plus or minus 1, then the probability distribution of the Gibbs state follows this distribution. And so here the goal becomes, we're given a bunch of samples of this probability distribution, and our goal is to measure the lambdas. And as it might suggest from the name Markov random field, these Gibbs states satisfy something called the Markov property in the classical setting, which I've described here. So the idea is that if we have some subset of the space here, it's just one qubit, and I condition on all of its neighbors. So here I've just conditioned on these neighbors being +1 or -1. And upon doing so, the distribution sort of splits into, or decomposes, so that the blue qubits here are independent of the qubit that we are looking at, so this pink qubit here. And this is easy to see because you can just write this probability distribution as the product of terms that don't have anything to do with the particular qubit I that we were considering, and the rest of the qubits. And you can see that if you set all these neighbors to either +1 or -1, then just naturally it's decomposed into a product that depends on xi and a product that doesn't depend on xi. And so this is how you would see this. Now, given this Markov property, it's a very strong property because it just allows you to solve Hamiltonian learning in the classical setting. And so what you would do is, if you wanted to learn some lambda ij, what you would do is you would get a bunch of copies of your row. So here I have one sample, one copy of row, but I'll get a bunch of samples. And then what I'll do is I'll condition. So I want to learn lambda ij, so I'll condition on all of the adjacent bits to I and j, and I'll condition on them being 1. And when I do this, when I condition on these both being 1, what I'm doing is I'm just selecting the samples where they match that they're both +1. And upon doing that, then the resulting distributions on the pink qubits and the blue qubits are independent. And this is important because what I've done is I've just separated a constant sized subsystem from potentially a large rest of the space. And so at this point, what all I need to do is I can just learn this distribution. And it needs some working out that I'm not going to explain. But once you have this constant size subsystem, the problem becomes basically it's just a calculation to show that this number of samples suffices to learn lambda ij to sufficient to epsilon error as desired. Right. So yeah, and the reason that we only need log m copies here is that we can reuse samples, and then after we can perform the same algorithm to learn all of the lambdas with the same samples, and then we can just take a union bound to make sure that the probability that all of them are right is small. So I'm not going to explain the details, but are there any questions about how you get the classical learning, how you solve this classically? Okay. Now I'm going to discuss how we get our results in the quantum high temperature setting. So the problem that we immediately run into if we try to do this quantum Hamiltonian learning problem is that we would want to try to generalize the approach that I just sketched before, where we use the Markov property to restrict to a constant size subsystem. But the issue is that the Markov property doesn't hold for general Hamiltonians. Now, luckily, we have decided that we're going to restrict to a setting, which the high temperature setting, where an approximate version of the Markov property does hold. So in particular, I'm pulling from this work of Kuwahara, Kato, and Brandau. And so here's the strict generalization is a bound on the conditional mutual information, but the bound that's more useful for the Hamiltonian learning problem is this one about effective Hamiltonians. So it's maybe if the experts can probably understand what's going on here, but just the way that you should interpret this bound is it means that what you can do is that in the high temperature setting, you can take, if you wanted to learn a term that's supported on A, then what you can do is you can take a ball around it that's the size log 1 over epsilon, or like a constant times log 1 over epsilon. And then what you do is you just ignore everything outside of this ball and just pretend that your Gibbs state that you were given was just A union B. And then once you have this A union B, then you can try to learn the Hamiltonian term related to A. And at that point, the Hamiltonian term that you get is actually going to be close to the Hamiltonian term of the global, the whole state, or the original Gibbs state. And so basically what this does is just using this as like a black box, it allows you to restrict to a subsystem that's in the same way that you would in the classical setting. However, the issue is that this this ball could be as large as like log 1 over epsilon to the size of the spatial dimension. So it could be log 1 over epsilon to the d. And this is not small enough to just do something like state tomography or something to learn this A union B state. Right? It's sort of not small enough for our purposes. So it can give you a quasi-polynomial time algorithm, but it doesn't suffice in general. It doesn't suffice for anything polynomial. So what we do is we look a little bit closer at what's going on. And in particular, what we're going to use is that this fact that if we know these marginals, which is sort of, I guess, the expectation of an observable here. So this is trace EA rho of X, where EAs are the terms of the Hamiltonian. If we know these values, these marginals, then it determines the value of the coefficients. And so this is sort of a fact that's related to the fact that Gibbs states are the maximum entropy state that preserves the marginals. So basically, like you can write an optimization problem where rho is just something that depends on the marginals. So it's sort of related to this notion. And so given this, and one can sort of think of the idea that, okay, so these marginals are actually easy to estimate, right? Because all you need to do is you need to just measure rho in the right eigenbasis, and this gives you a random variable that can estimate this trace. So we can actually get estimates of these easily. And however, the thing that we want, lambda A, it is a function of these marginals. And so maybe there's some way of taking estimates of the marginals and then deducing estimates of the coefficients. Now, the thing that one would need to check in order for this strategy to hold is that if you get some estimates, like get something close to the right marginals, then you can also deduce something close to the right coefficients, right? So this is what I've written here. It's a Lipschitz bound, essentially. So I say that like we would need that if our marginals are close for some lambda that's close to our, for some lambda that's, then this lambda tilde is going to be close to the actual coefficient. And I guess like the way to sort of manipulate this to what we want is that this is sort of, so it suffices to show this to get like a sample complexity bound. And what this basically, something else that suffices is to show that this map that takes the this map from the marginals to the coefficients, you want to show that this has like bounded derivative, but here it's a vector valued function, so it's bounded Jacobian. So it's a little bit weird yet having this map from the marginal to the coefficients. So instead we can analyze the map from the coefficients to the marginals, and then show that the corresponding Jacobian has sort of lower bounded, is lower bounded. So this is I think an equivalent statement. Maybe it just implies. Or in other words, that the Jacobian inverse is bounded. So all this is just to say that the thing that we ultimately would want is that using just standard calculus, that we just want a bound on the inverse of the Jacobian of the map from the coefficients to the terms. And this can be made precise. And this is essentially what this AAKS paper proves, although they do it in a different norm, and then they call it proving strong concavity of the log partition function. But this is essentially what's going on. Are there any questions? Okay. So, so from what I've just stated, all it basically boils down to is just considering this map that takes the coefficients to the marginals and trying to bound some function of its derivative. Okay. And so what we do now from here is that we can use the sort of structural results used to achieve these other Markov property approximations, and instead use it to try to understand how the terms and the marginals relate. And we use this argument known as cluster expansion. And what this cluster expansion argument just says is that if you take the log partition function, which I've written here, and then you write its multivariate Taylor series expansion, which I've written here, although I haven't defined this notation, but it's fine, that this Taylor series expansion converges for in the high temperature regime. And upon knowing that this this log partition function can be written as like some power series, then we can write our marginals also in terms of this power series because it's just a derivative of the log partition function. So it's a rescaled derivative. And so this means that we can write the marginal in terms of basically just like a Taylor series expansion. And in fact, the coefficients of these polynomials are things that we can compute. And so now this is nice because we just have a system of polynomial equations. We've reduced this problem to a system of polynomial equations where on one side, there are the things that we can estimate. And on the other side, they're the things that we want to find. So here I've just written like the first two terms of the sum, but it also goes to, there are also higher order terms as well in the lambdas. Okay. Now, moving from here, it's useful to think about sort of the limiting regime as beta goes to 0. And as beta goes to 0, in fact, we can sort of stop thinking about all these terms. And then we just have that if we can estimate these marginals, then we can estimate the term. Then the terms are just the marginals like over beta. So all that we need to get estimates sort of intuitively is just to estimate all the marginals to beta epsilon error, and then just divide by beta to get the lambdas to epsilon error. And this gives you the right sample complexity bound. So this is sort of the idea. And more formally, we do use this to show the desired bound on the Jacobian that gives us a sample complexity, that gives us the optimal sample complexity upper bound. And the reason why this is true is that if you just look at the Jacobian, the way that it's, what it is it's just beta times the identity plus some beta squared order terms. So if you just make beta sufficiently small, then the first term dominates. And then we get that the Jacobian sort of behaves like beta times the identity in the sense that its inverse is not too large. So I've shown that because we were able to express our marginal as like a polynomial equation, or I guess as of this moment, a power series, that gives us the sample complexity bound that we want. To get the time complexity bound, we do something basically pretty similar, which is that we first of all, we estimate all of our marginals to beta epsilon error, as we suggested in the beta to 0 limiting case. And then after we perform this quantum portion, then all that we need to do is a classical algorithm. And the goal of this classical algorithm is to find an x, a set of coefficients such that this approximation is satisfied. So we want to find an x such that basically the marginals match, except instead of the marginals, we write the marginals as a power series, and we truncate the power series to this frac m, which is like something like log 1 over epsilon. So we truncate this, and now we just have a polynomial, and we just want to find some x such that this polynomial is close to the estimates that we found from the quantum part. And through this series of approximations, this shows that the marginals corresponding to the coefficients lambda match to the marginals corresponding to the coefficients of x. And as we discussed earlier, because we proved this Jacobian bound, this will give you that lambda and x are close enough. So this is sort of like a sketch of how the analysis would work. And something to note is that when we truncate at this point, this is basically a refinement of what we were doing before when we were truncating to a log 1 over epsilon sized ball around a particular term. So this is sort of the same thing. Right. Okay. So equivalently, right? So now these are just, this is just a problem of solving a system of polynomial equations. So the way that we do this is we just rewrite it so that the goal is to find an x such that f of x is small, where f of x is just comes from the difference of these two terms. So we want basically the difference to be small. And then this is just a problem of finding zeros, or I guess like roots. So we just use a root finding method, the Newton's method for root finding, which is just an optimization method that that gives you the right answer in like log 1 over beta epsilon iterations. So I guess I'm out of time, so I'll stop here. I can discuss if you'd like why the result that we get is optimal, or some these other pieces of the table if you want, but thank you.
So we have time for questions. Feel free to speak up or type it.
Hi, Ewin. I wanted to ask a question on the quantum part. When you are estimating all these expectation values, are you using something like this classical shadow tomography results, or how do you do that?
Wait, sorry, can you say that again?
So, like, you described your algorithm, and you said that you just need to like estimate all these expectation values for these local observables, which correspond to Hamiltonian terms, and that you can do it with log n samples times this like polynomial beta epsilon. And there, like, do you need to use any of these like classical shadow tomography techniques, or how do you do that?
So you don't need to do any sort of shadow tomography. All that you need to do is just to so whenever you I guess try to whenever you have a sample, you can reuse that sample for like a fraction of n many different terms, just because you can find a bunch of terms that have sort of disjoint support, and then you can use one sample to find to sort of count as an estimator for all of these different terms, because you're measuring different parts of the space in order to get these expectation values. And so you don't need to use anything fancy. Does that make sense?
Yeah, thanks.
I have a question. So I don't know if you mentioned this during the talk, but does your method also give a good bound on strong convexity of log partition function at, I don't know, at high temperatures?
I believe it does. I believe the strong convexity is, so I guess we don't currently have it. We currently don't state that we have it. But essentially what I wrote here,
right.
This bound here, it shouldn't be too hard to adapt this to show that the same thing holds for the, or I don't know if it directly implies the strong convexity bound, but I think the same analysis gives you it, but I would need to check.
Oh, you would expect 2 over beta to be the, okay, got it.
Yeah,
Right.
I would expect this.
So since you offered, maybe I can ask. So the lower bounds, they're based on what are they based on?
So these lower bounds are fairly straightforward. So I guess this classical one and our work are both classical Hamiltonians, and so these are just samples from probability distributions, and so what it is it's basically I believe the Hamiltonian basically looks something like maybe like 1 plus epsilon, 1 minus epsilon, and then minus 2 or something like this. Like, so this would be your Hamiltonian. And then when you take beta to be large, so you would need to distinguish which one is which. So there's maybe, I guess, 2 options, right? You need to distinguish these 2 Hamiltonians. And because you have this term that's sort of the large portion of your magnitude, you're very rarely going to see either of these in a sample. And so basically, this gives you one of the cases where it's like it gives you some, like the epsilon, the e to the 2 beta over epsilon squared, and then you can do the other direction where you have there's I guess a different case for the 1 over beta squared epsilon squared, and at that point you use I guess I think it's Fano's inequality. You use some information theory to just extend it to the case where you have n copies of the state. So it's I guess it's like fairly standard stuff.
Yeah. Yeah.
Ewin?
Yeah, sorry, go
Does
ahead.
this work? So I have a question about the solving the polynomial equations. So you use this like Newton-Raphson method. How do you know that? How do you know that it will converge? I mean, this might be a basic like optimization question, but how do you know that it'll find a solution in a certain amount of time?
So you can show that it converges if you have a bound on sort of the second order terms of so like if you have a good bound on the derivatives of the polynomial of the system of polynomials, then this means that the Newton's method will converge. And I didn't discuss this at all, but your polynomials, this polynomial expression obeys nice properties because sort of from the fact that the corresponding Taylor series converges, these polynomials have sufficiently nice properties that you can show that these sort of higher order derivatives are bounded.
I see. And is this
Yeah.
where the Jacobian, the bounded Jacobian inverse also comes in, or that's something separate?
Right. So this isn't actually the structure of the analysis. We just sort of directly show that it gets you a lambda. It gives you a value of x that's close to the right coefficients. But yes, we use the bound on the Jacobian, or I guess we use a bound on the derivative after the Jacobian. I don't know what that one's called. But we use those bounds.
Well, thanks.
Mm-hmm.
Even I have one more question regarding. So you motivated your talk with some recent results of Brandao and Kotaro and some third author, and so I was wondering if, but later it seemed that you didn't use that result. Like it seemed that it's like a first attempt, but it kind of motivates intuitively what you are doing makes sense. But then it seems that in your algorithm and analysis, you actually didn't use this Kuwahara-Kato Brandao result. Is that true?
So we basically use kind of the same or a similar analysis. So so sort of the one of the key ideas of this work is using this cluster expansion thing that I mentioned, which is I guess it comes from a paper of, I think it comes from a paper of Kuwahara and Saito. So basically we use a similar analysis. We just try to change it to get a Hamiltonian learning result. Yeah, so yeah.
So you use the analysis rather than the result. Okay.
Right.
Would you know if these techniques could go to low temperatures, or something else that could go to low temperatures?
So I don't think so, because this like multivariate Taylor series expansion stuff immediately breaks. Yeah, the one thing that's nice about these results is that it doesn't actually require low spatial dimension. It requires sort of a slightly different thing, but it's sort of more general, a more general statement. But I guess it's like not, yeah, it's not the generalization that is like the best for us, but you know, it's something.
Thanks.
Mm-hmm.
Any more questions? Okay, if there's no question, let's thank Ewin for a talk again. Thanks a lot. And so I think the plan now is that we have a short break, half an hour. People can go and get coffee or dinner if they're in Europe like me. And then we resume in half an hour at 11:45. Is that the 11:45? Yeah. Okay. Good. So 11:45. The Zoom is the same, so you're welcome to stay. And we'll just resume. Okay. Have a good break.